Problem 12. Critical radius of insulation for steam pipe. A 160 mm diameter pipe carrying saturated steam is covered by a layer of lagging of thickness 40 mm having K 0.8 watt per meter degree Celsius. Later, an extra layer of lagging 10 mm thick having K 1.2 watt per meter degree Celsius is added. If the surrounding temperature remains constant and heat transfer for both the lagging material is 10 watt per meter square degree Celsius, determine percentage change in the rate of heat loss due to extra lagging layer. So let us solve this problem. First, let us discuss the schematic of this problem. In the given problem, there is a steam pipe shown in the black color of some finite thickness, and it is carrying steam, let's say having temperature T infinity I, and the presence of steam is shown by this dotted circle. This steam pipe is provided with an extra single lagging. It is also called as insulation material layer. It is also called as lagging in other way. Let's say thermal conductivity of this lagging one is K1, and it is exposed to the surrounding fluid having temperature, let's say T infinity O, and convective heat transfer coefficient H infinity O. Here hot fluid is inside and cold fluid is outside. So by virtue of this temperature difference, heat transfer will take place from inside of the fluid to the outside. Let's say at the rate of Q1. The surrounding fluid is represented by green dotted circle. Now, in second case, the same steam pipe with lagging 1 is provided with another lagging or insulating material 2 having thermal conductivity, let's say K2, and it is exposed to the same environment having outer temperature T infinity O and convective heat transfer coefficient T infinity O. Let's say outer radius of this steam pipe is R1 and outer radius of insulation 1 is R2 and outer radius of insulation 2 is R3. And let's say by virtue of the temperature difference between saturated steam and surrounding fluid, rate of heat loss from this composite pipe is Q2. Now let us draw the equivalent electrical circuit for this arrangement. So in case 1, the flow quantity is heat loss rate Q1 and first thermal resistance will be offered between, let's say the cylinder surface, the steam pipe temperature is T, the outer insulation temperature is T1. Similarly, in case 2 T1, and outer surface temperature of insulation 2 is T2 and surrounding temperature is T infinity O. So in case 1, the first thermal resistance will be offered between temperature T infinity I and the first thermal resistance will be offered between temperature T infinity I and T. And it will be by conduction. Here, no thermal resistance will be offered by fluid film, steam fluid film, because convective heat transfer coefficient for steam is not given. So unless otherwise the H infinity value for steam is given, we cannot determine whether it is going to offer thermal resistance or not. So thermal resistance will be offered between temperature T infinity I and T1, RT1 by insulation material 1. Then second thermal resistance will be offered between temperature T1 and T infinity O by surrounding fluid layer, and it will be convective thermal resistance RT infinity. In second case, the flow quantity will be Q2. The first thermal resistance will be offered between temperatures T infinity I and T1, and it will be RT1. Second thermal resistance will be offered between temperature T1 and T2. It will be RT2. Both these thermal resistances will be conductive thermal resistances by insulation 1 and 2 respectively. And final thermal resistance will be offered between outer surface of the insulation 2 and surrounding fluid. And finally heat will be dissipated. So this way we could draw the equivalent electrical circuit for steam pipe with insulation 1 and steam pipe with insulation 1 and 2. Now let us enlist all the given things. From the problem it is clear outer diameter of the steam pipe is given, lagging 1 and lagging 2 thicknesses are given as 40 mm, 10 mm respectively, and their thermal conductivities are given. And finally, convective heat transfer coefficient value of surrounding fluid is given. So outer radius of cylinder R1 will be 80 mm, 0.08 meter. Thickness of insulation 1 is given 40 mm. Its thermal conductivity K1 is given 0.8 watt per meter degree Celsius. So outer radius of insulation 1 will be 80 plus 40, 120 mm, 0.120 meter. Thickness of insulation 2 is given as 10 meter. So outer radius of insulation 2 will be 120 plus 10, 130 mm, that is 0.130 meter, and its thermal conductivity K2 is given 1.2 watt per meter degree Celsius, and the convective heat transfer coefficient of the surrounding fluid to which the entire pipe and insulation systems are exposed is given as 10 watt per meter square degree Celsius. Now let us first take assumptions. So assumption 1 will be one dimensional steady state heat transfer. Number 2, heat transfer in radial direction only since it is cylindrical. Number 3, no heat generation. Number 4, steam pipe surface and insulation 1 and 2, they are forming a composite arrangement, composite system. So between interfaces, due to imperfect contact, thermal contact resistance may come into picture. And problem does not talk anything about the thermal contact resistance, so we will neglect it. So no or negligible thermal contact resistance. Then homogeneous and isotropic material of pipe and insulation. So because of this assumption, K and H values are going to remain constant. Now let us enlist what is to be found out. We are supposed to find out what is the change of heat transfer in second case, percentage increase or decrease in heat transfer. So basically we are supposed to find out Q2 minus Q1 over Q1 into 100. Now let us do the detailed calculations. So first let us find out Q1, that is heat loss from the pipe with single insulation. Steam pipe with single insulation. So let us find out heat loss in this case Q1. Now since we know under one dimensional steady state condition, rate of heat loss from the steam pipe Q1 will be rate of heat transfer from steam and pipe to the outer insulation will be equal to rate of heat loss from insulation 1 outer surface to surrounding fluid. In terms of temperature, it can be T infinity I minus T1 over RT1 is equal to T1 minus T infinity O over RT infinity 1. Since I don't know the value of T1, so I can express the Q1 in terms of T infinity I minus T infinity O over RT1 plus RT infinity O1. Let us say this is equation number 1. In this equation, T infinity, in this equation, RT1 is conductive thermal resistance of insulation 1, and it can be given as 1 over 2 pi K1L log of R2 over R1. Let us refer the diagram. This is RT infinity, RT1 will be conductive thermal resistance of this insulation 1 in case 1, and RT infinity O1 will be convective thermal resistance of surrounding fluid, and it can be given as 1 over H infinity O into AO, and for case 1 it can be given as H infinity O into 2 pi R2 L. Now, considering these individual values of RT1 and equation 3, I can write them as T infinity I minus T infinity O over, let us put all those values, 1 over 2 pi, the value of K1 as 0.8 into L log of R2 is 0.120, R1 is 0.08. This is conductive thermal resistance of insulation 1 plus 1 over the value of H infinity O is 10, 2 pi L, and value of R2 is 0.12. Since 2 pi L is common and not known to me, so let us take it out. Q1 will be T infinity I minus T infinity O So after taking this value out, 2 pi L, it will go to the numerator, and the denominator quantity comes out 1.340. So this way the value of Q1 comes out in this form of equation. Let's say this is equation number 2. Now let us consider case number 2. Steam pipe with insulation 1 and 2. So in this case the heat loss rate is Q2. So under one dimensional steady state condition, rate of heat loss from the composite pipe in case 2 will be equal to rate of heat loss from steam to the insulation 1 will be equal to rate of heat loss from insulation 1 outer surface to insulation 2 surface, and finally from insulation 2 surface to outlet surface. In terms of temperature, T infinity I minus T1 over RT1 is equal to T1 minus T2 over RT2 is equal to T2 minus T infinity O is equal to RT infinity O in second case. So same thing we have represented in the form of electrical equivalent circuit. So you can see here. Now once again let us express Q2 in terms of steam temperature T infinity I minus surrounding fluid temperature T infinity O. So it will become RT1 plus RT2 plus RT infinity O second case. Now once again RT1 is conductive thermal resistance of insulation 1, and it can be calculated as 1 over 2 pi K1L log of R2 over R1. RT2 is conductive thermal resistance of insulation 2, can be calculated as 1 over 2 pi K2L log of R3 over R2, and finally RT infinity O convective thermal resistance of fluid in case 2, 1 over H infinity O, and in the second case the outer radius of insulation is 2 pi R3L. Putting all those values of, let's say this is equation number 3. So putting all those values of RT1, RT2 and RT3 into equation number 3 will give me Q2 as T infinity I minus T infinity O over 1 over 2 pi K1 is 0.8 into L log of 0.12 over 0.08, this is RT1, plus 1 over 2 pi K2 is 1.2 log of 0.13 over 0.1. This is RT2, and finally 1 over 10 into 2 pi into R3 is 0.13 into L. Once again, the 2 pi L is common, taking it to common and taking it to the numerator. And after calculation, the expression for Q2 will be T infinity I minus T infinity O 2 pi L over, this will give me 1.343. Let's say this is equation number 4. Heat loss from the system in second case. Now I am supposed to find out percentage change in heat transfer, that is Q2 minus Q1 over Q1. So Q2 is T infinity I minus T infinity O 2 pi L over 1.343 minus T1 is T infinity I minus T infinity O 1.340. Here it is 2 pi L over Q1 T infinity I minus T infinity O 2 pi L over 1.340. And we are interested in percentage change. So this entire term will be multiplied by 100. So after solving this, I can get Q2 minus Q1 over Q1 into 100 as minus 0.223%. Now here minus sign is appearing, mind well. So negative sign indicates that heat loss is decreasing due to second layer of lagging. Q2 is less than Q1, that is why this Q2 minus Q1 over Q1 into 100, this percentage variation is coming in negative. So this way we could solve this problem.